The singularities that we discuss in this video are the real number analogs of singularities that are familiar in complex analysis. We don't need to know any complex analysis for this video. The singularities here are isolated in the sense that there is no singularity that comes arbitrarily close to them. We have three ways in which these singularities can occur. We will be talking about three types of singularities. First one is called removable, and I'll explain why that is the case in this video soon. A removable singularity is basically seen on the graph as a hole or cut or a point gap, a missing point on the graph. The other kind, the second kind, is a jump singularity, and that turns out to be non-removable, and I'll discuss that in some other video. And a singularity that's more complicated than either of these two, essential singularity, it will be the subject of also a separate video. Okay, let's talk about removable singularities, starting with this function f of x, which, as you notice, is not defined at x equal to 1, because putting 1 for x gives us a 0 in the denominator, and that's not mathematically meaningful. As long as x is not equal to 1, we can simplify this function by factoring the numerator, and noticing that I can cancel the term x minus 1, and this x minus 1 is in fact the thing that was causing the problem with the division by 0. What's left is x plus 1, and that is a well-defined function. Let's call it g of x. This g of x has no gaps or hole. Its graph is a straight line. It's a continuous function. And notice that g of 1 is in fact defined, and it is equal to 2 in this case. So we've seen that these two functions are the same, exactly the same function everywhere except at x equal to 1, where f is not defined, but g is defined, and in fact g of 1 is equal to 2. Now, if I draw the graph of f, basically what I'll do is to graph g and skip a point on that graph. So let's draw a quick here's 1, and now I draw a graph that is a straight line but is missing a point. This is the graph of f, and the straight line here is just x plus 1, g of x, without 1 point. There is only one way to fill that hole in the graph, and that is by assigning the value f of 1 to equal g of 1, namely f of 1 equals 2. With this, we can fill up the hole and make a continuous function out of that. Any other value than 2 would be either above or below the line and would leave the hole intact. But what if we don't have a nice g of x that we can get by algebraic simplification? Here's a case in point, f of x equal to sine x over x. This function is also not defined at x equal to 0 because we can't divide by 0. But what we can do is to use a graphing calculator or a computer to plot a picture of it. I've done that and gotten this curve here. You'll notice that it is a continuous, nice, smooth curve, and of course it has a gap where 0 is. So let's see what we can learn from this graph. Notice that the graph appears to be moving up towards 1. It happens whether I go from the left or from the right. In both cases, the graph appears to approach the number 1 up here. So I can fill up the gap by assigning 1 to sine of x over x. Let's say that let's call that the limit as x goes to 0 of sine of x over x equals 1. We can actually calculate this limit using L'Hopital's rule, which I will talk about in a separate video. We don't need to discuss that here. So everything seems to boil down to limits. F of x may not be defined at x equal to s, some point like 0 or 1 that we saw before, but it could be any point s depending on the function f of x. If f of x is not defined at this point s, but we take its limit either using algebraic simplifications or L'Hopital's rule or whatever, and we come up with a number L, then assigning L to f of s, or defining f of s equal to L, will fill the hole. This feature allows us to remove the singularity by filling the hole. Once the hole is gone, so is the singularity. We had two examples of x squared minus 1 over x minus 1 and sine of x over x. The first one has a removable singularity at 1, and the second one has a removable singularity at 0. It may not seem like calculating limits and removing singularity, filling holes, that kind of thing, using algebra or L'Hopital's rule is such an exciting or interesting idea, but let's not jump to conclusions. This whole idea of taking limits and removing singularities is absolutely essential in the definition of derivatives, and so let's talk a little bit about that. We start with a simple function like x squared, which is very familiar. It's defined for every x. Let's pick an x like x equal to 1, then f of 1 is 1, and f prime of 1, its derivative, is defined as the limit of this ratio here, which is called the difference quotient or difference ratio of f of x. Notice that if I put f of x in, f of x equals x squared, in for f of x, I get x squared here. F of 1 is 1, so that's 1 here, and I get x squared minus 1 over x minus 1, and that is exactly what we had earlier when we were talking about algebraic simplification. We calculated this to be equal to 2, and that means f prime of x squared at x equal to 1 is 2, something that you can easily figure out using the power rule also. Okay, for the simple function x squared at x equal to 1, we figured out that removing the singularity of the difference ratio at x equal to 1, which is the same thing as filling the hole, is tantamount to finding the derivative of x squared at x equal to 1. The same idea works for other functions. It doesn't have to be just x squared. Pick f of x equal to sine of x. and see what happens to the derivative of f at x equal to 0. Derivative of f at x equal to 0, f prime of 0, is given by this expression, sine of x minus sine of 0, that's f of x minus f of 0 divided by x minus 0. But since sine of 0 is 0, this reduces to this. The same thing that we discussed a little bit earlier, and we determined that its value is actually equal to 1. Now we see the same thing for x squared happening for sine of x. The derivative of sine of x at x equal to 0 is found by filling the hole in the difference ratio at x equal to 0. Let me stress that we find f prime not by removing any singularities in f, because f is continuous and smooth and there is no singularities there, no gaps, no holes. We calculate f prime by removing the singularity in the difference ratio of f. Let's check to be absolutely clear about this. Let's pick another function that we haven't dealt with so far, like x squared minus 3x. It's still something simple. Pick an x, any x, let's say x equal to 2. F of 2, we put 2 in here and calculate minus 2. That's f of 2. So that's this quantity here. Alright, what about the difference ratio? The difference ratio is f of 2 here and f of x here. We get something like this. This is obviously not defined when x equal to 2, which gives us a 0 in the denominator. So to figure out the limiting value that removes the singularity at x equal to 2 in the difference ratio, let's use algebra. The limit of the difference ratio is just f prime of 2, so let's keep that in mind. We know that minus minus 2 becomes plus 2. We can factor the numerator. X squared minus 3x plus 2 breaks into x minus 2 times x plus 1. Now this is a good thing because we can cancel x minus 2 from numerator and denominator, and that gets rid of the 0 in the denominator. What's left is x minus 1, and limit as x goes to 2 of x minus 1 is just 2 minus 1, or 1, which means that assigning the value of 1 to the difference ratio, assigning the limit 1 to the difference ratio, removes the singularity and gives us a number f prime of 2 equal to 1. If you like, you can test this, test that this agrees, or check your answer with using the power rule. F prime of x, f of x being x squared minus 3x gives f prime of x 2x minus 3. And if I plug in 2 for x, I get 2 times 2, 4 minus 3. 4 minus 3 is 1. And that's the same thing that we got over here. For perspective, let's keep in mind that the power rule is not a replacement for this calculation. This type of calculation is really what's behind the power rule. So we should keep that in mind. Okay, one more thing to discuss is that removable singularities that we have talked about so far, they all seem to be difference ratios, but difference ratios in reality are just a subset of all the removable singularities. There are many others. Here's, for example, something that is not a difference ratio, and it is also not defined at x equal to 1 because natural log of 1 is 0. and if I put x equal to 1, I get 0 there in the denominator. But the way to deal with this is by using the properties of log or logarithm to simplify the expression. I can pull out the power 2 and make it a coefficient here. That way I get log 2 ln x instead of ln x squared, which is a good thing because now I can cancel the ln's and that way get rid of what was causing the 0 in the denominator. What is left is 2 over x, and if I put x equal to 1 in this, I get 2 over 1, which is 2. So the limit as x goes to 1 of f of x is 2, which means if I assign 2 to f of 1, I'll remove the singularity and fill the hole. And this is a good place to stop.